Hello there, and welcome to Cosmic Drift. Tonight, we're taking a gentle journey through our solar system, floating from world to world like a quiet traveler carried by the solar wind itself. We'll discover facts that feel as soft as starlight, as soothing as the rhythm of distant orbits, and as peaceful as the silence between planets. Some of what we'll explore will feel familiar, like the way sunlight takes 8 minutes to reach us, painting everything we see in the past. Others will surprise you, like how Saturn's rings sing with radio waves, or how Venus rotates so slowly that a day there lasts longer than a year. But each discovery will remind you that we live in a cosmic neighborhood more gentle and wondrous than we often remember. Tonight we'll drift through facts about gravity that holds worlds in perfect dance, about moons that waltz around their planets, and about the quiet beauty of ice and rock spinning in the darkness. You might find yourself settling deeper into rest, or simply letting these celestial stories wash over you like waves on a distant shore. If you enjoy these peaceful journeys through space and would like to join us for more nighttime explorations among the stars, feel free to like and subscribe below. Share your favorite cosmic thoughts in the comments if you'd like. But for now, all you need to do is get comfortable, let your breathing slow, and allow the gentle mysteries of our solar system to carry you wherever they may. Let's begin our drift through the cosmos. The sun breathes in an 11-year rhythm. Every 11 years, our star shifts from quiet to active and back again, like a cosmic heartbeat that's been steady for billions of years. During solar maximum, the sun's surface blooms with sunspots, dark patches that are actually cooler regions where magnetic fields tangle and twist. These spots appear and fade like slow fireworks, each one larger than Earth, each one a sign that our star is stretching and yawning in its magnetic sleep. During solar minimum, the sun grows calm, the sunspots fade to almost nothing, and the solar wind gentles to a whisper. The aurora that dance around our poles grow fainter, as if the Earth is settling into a deeper rest. This rhythm has been traced back through centuries of observation, a reliable pulse in our cosmic home that reminds us even stars have their seasons of activity and peace. Right now, we're climbing towards solar maximum, but the sun's fury is gentle compared to other stars. Our sun is what astronomers call a yellow dwarf, stable and mild-mannered. It burns its hydrogen fuel at just the right pace to last 10 billion years, giving life on Earth all the time it needs to unfold slowly, like a flower opening across geological ages. Mercury has ice hiding in the shadows of its poles. It seems impossible on the planet closest to the sun, where daytime temperatures soar to 800 degrees Fahrenheit. But Mercury spins slowly, taking 59 Earth days to turn once, and it has almost no atmosphere to trap heat. So when night falls on Mercury, it falls completely. Temperatures plummet to minus 300 degrees, colder than anywhere on Earth. At Mercury's poles, some craters never see sunlight. They've been dark for billions of years, and in that eternal shadow, ice has collected like cosmic snow. Water arrived on comets and asteroids, and in those permanently shadowed regions, it stays frozen, patient, and still. Spacecraft have detected these ice deposits, gleaming faintly in radar images, a reminder that even the most sun-baked world in our solar system holds pockets of coolness and calm. Mercury also has the most eccentric orbit of all the planets. Sometimes it races close to the sun, sometimes it drifts farther away, its speed changing like a cosmic dancer moving to music we can barely hear. This strange orbit puzzled astronomers for centuries until Einstein's theory of relativity explained the subtle tug of curved spacetime that makes Mercury waltz in its particular way. Venus spins backwards beneath clouds of pearl. If you could stand on Venus and watch the sun rise, it would appear in the west and set in the east, the opposite of every other planet except Uranus. Venus rotates so slowly and in reverse that a single day there lasts 243 Earth days. Yet it completes its orbit around the Sun in only 225 Earth days, meaning a day on Venus is actually longer than a year. The backward spin might have come from an ancient collision, a cosmic accident that knocked Venus off its normal rotation billions of years ago. Or perhaps the thick atmosphere and the sun's gravity gradually slowed and reversed the planet's spin over eons. The exact cause remains a gentle mystery, like so many things in our solar system. Above this slow spinning world, clouds of sulfuric acid drift 40 miles high, reflecting sunlight so brilliantly that Venus shines as the brightest object in our night sky after the moon. These clouds move fast, racing around the planet in just 4 days, driven by winds that howl at 200 miles per hour. Yet down at the surface, the air barely stirs. The thick atmosphere creates a blanket so heavy that surface winds move no faster than a gentle breeze. Beneath those racing clouds, the surface pressure is 90 times greater than Earth's, like being half a mile underwater. The greenhouse effect has run wild there, trapping heat until the surface temperature reaches 900 degrees, hot enough to melt lead. Yet from space, Venus appears serene and beautiful, wrapped in smooth white clouds that hide the furnace world below. Our moon moves away from us by about 1.5 inches each year. This gentle retreat has been going on for billions of years, ever since the moon formed from the debris of a Mars-sized world that collided with early Earth. Back then, the moon loomed huge in the sky, maybe 10 times closer than it is now, raising tides hundreds of feet high and making days only 5 hours long. As the moon pulls away, our days grow longer. The Earth's rotation gradually slows, adding about 20 seconds to each day every million years. The moon's retreat is powered by the tides themselves. As Earth's oceans bulge toward the moon, friction steals a tiny bit of energy from our planet's spin and transfers it to the moon's orbit, pushing it gently outward like a cosmic slingshot in slow motion. This dance between Earth and moon has been shaping both worlds. Early in Earth's history, the much closer moon would have kept our planet's axis stable, preventing wild climate swings that might have made life impossible. The moon also stirred Earth's early oceans with massive tides, perhaps helping mix the chemicals needed for life to begin. Billions of years from now, the moon will have drifted so far that it appears much smaller in the sky. Total solar eclipses will become impossible because the moon won't be large enough to cover the sun completely. But that's so far in the future that the sun itself will have changed, swelling into a red giant that transforms our entire cosmic neighborhood. Mars has seasons just like Earth, but each one lasts twice as long. A Martian year stretches for 687 Earth days, so spring, summer, autumn, and winter each unfold across many months. The planet's axis tilts at almost the same angle as Earth's, 25 degrees compared to our 23. So the seasonal changes follow familiar patterns, just stretched out in time like a slow, patient cycle. During Martian winter, carbon dioxide freezes out of the thin atmosphere and falls as snow, accumulating in white polar caps that advance toward the equator. In summer, this dry ice sublimates directly back to gas, and the polar caps shrink again. The atmosphere actually changes density with the seasons as this carbon dioxide cycles between solid and gas, making the planet breathe in its own gentle way. Mars also experiences dust storms that can cover the entire planet, lasting for months at a time. These begin as small whirlwinds but can grow to engulf the whole world in a soft red haze. During global dust storms, the surface disappears completely from view, and temperatures even out as the suspended dust distributes heat around the planet. When the storms finally settle, Mars emerges clean and refreshed, its rocks and valleys scoured by the scouring wind. The planet's two small moons, Phobos and Deimos, race around Mars in orbits so fast they seem to chase each other across the Martian sky. Phobos completes 3 orbits every Martian day, rising in the west and setting in the east. Deimos moves more slowly but still outpaces Mars's rotation, so it rises in the east like our moon but takes more than 2 days to cross the sky. These tiny moons are probably captured asteroids, dark and potato-shaped, tumbling slowly as they orbit like cosmic dice thrown across the red planet sky. Jupiter is a failed star that became a gentle giant instead. If Jupiter had gathered just a bit more mass during the solar system's formation, maybe 80 times more, nuclear fusion would have ignited in its core and we'd live in a binary star system with 2 suns. Instead, Jupiter became something more subtle and beautiful, a world of swirling clouds and hidden depths that has spent 4.6 billion years slowly cooling down from its formation. Deep inside Jupiter, the pressure grows so intense that hydrogen becomes metallic, flowing like liquid mercury in Earth's gravity, but under conditions we can barely imagine. This metallic hydrogen ocean generates Jupiter's powerful magnetic field, which stretches millions of miles into space and traps radiation in belts around the planet. The auroras that dance around Jupiter's poles are thousands of times more powerful than Earth's northern lights, painting the giant planet's night side in curtains of blue and ultraviolet fire. Jupiter's Great Red Spot is a storm larger than Earth that has been raging for at least 400 years, maybe much longer. It's an anticyclone spinning counterclockwise like a cosmic hurricane in slow motion, with winds reaching 300 miles per hour at its edges. The storm appears red because of chemical compounds in Jupiter's atmosphere, but the exact chemistry remains a mystery, one of many gentle puzzles that Jupiter holds in its swirling depths. This great storm has been shrinking over the past century, slowly growing smaller and more circular, though no one knows if it will eventually disappear or simply change its shape. Other storms come and go on Jupiter, some lasting years, others only months, all of them dwarfing any weather system Earth has ever seen. Yet from a distance, Jupiter appears peaceful, its bands of clouds flowing in elegant patterns like brushstrokes on a cosmic canvas. Saturn's rings are made of countless ice particles, each one following its own perfect orbit. From Earth, the rings appear solid, but spacecraft have revealed them to be more like a cosmic snowstorm frozen in time. Billions of chunks of water ice, ranging from tiny snowflakes to boulders the size of houses, all spinning around Saturn in formation so precise it seems choreographed by invisible hands. The rings are incredibly thin compared to their width. If you made a scale model with rings the size of a football field, they would be thinner than a sheet of paper. This thinness comes from Saturn's gravity and the gravitational influence of its many moons, which act like cosmic shepherds, keeping the ring particles confined to narrow bands and preventing them from spreading out into space. Within the rings, waves and patterns flow like ripples on a pond. Some are caused by Saturn's moons tugging gravitationally on the particles. Others form when particles clump together temporarily, creating braids and spokes that appear and dissolve again. The Cassini spacecraft detected that the rings actually make sounds, radio waves generated by electrical charges dancing between the particles. A cosmic music too low for human ears, but hauntingly beautiful when translated into audible frequencies. The rings may be much younger than Saturn itself. While the planet formed 4.6 billion years ago with the rest of the solar system, its magnificent rings might be only a few 100 million years old, relatively recent in cosmic terms. They could be the remains of a moon that wandered too close to Saturn and was torn apart by tidal forces, or perhaps the debris from a collision between two of Saturn's moons scattered into orbit like celestial confetti. What makes this possibility even more poetic is that the rings are slowly spiraling inward, raining down onto Saturn's atmosphere like the gentlest snowfall. In perhaps 100 million years, they may be gone entirely, leaving Saturn as just another gas giant without its crown of ice. We are living during a brief window in cosmic history when Saturn wears its rings, witnesses to one of the most beautiful sights our solar system has to offer. Saturn itself floats so lightly that it would bob like a cork if you could find an ocean large enough to hold it. The planet is made mostly of hydrogen and helium, so fluffy and low in density that its average weight is less than water. This gives Saturn a dreamlike quality, as if it's not quite solid, not quite real, just a collection of gases held together by gravity's gentle embrace. Uranus rolls through space on its side like a cosmic bowling ball. While most planets spin upright like tops, Uranus rotates at a 98-degree tilt, essentially rolling along its orbital path rather than spinning. This unusual orientation means that each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness as the planet completes its 84-year journey around the Sun. Scientists believe this sideways tumble resulted from an ancient collision with an Earth-sized object that knocked Uranus over billions of years ago. The impact was so gentle that it didn't shatter the planet, but simply tipped it onto its side, where it has remained ever since, a reminder that even cosmic catastrophes can create something beautiful and strange. Uranus has rings too, though they're much darker and narrower than Saturn's brilliant bands. These rings were discovered by accident in 1977 when astronomers watched a star pass behind the planet. The star blinked on and off several times before and after disappearing behind Uranus, revealing the presence of thin rings that block starlight as they orbit. Unlike Saturn's icy rings, Uranus's rings are made of dark material, possibly organic compounds baked by radiation into something resembling charcoal. The planet's unusual magnetic field adds another layer of mystery. Instead of aligning with the planet's rotation like Earth's magnetic field does, Uranus's magnetic field is tilted 59 degrees from its rotational axis and doesn't even pass through the planet's center. This creates a magnetic field that tumbles end over end as Uranus rotates, generating auroras that dance in unexpected places across the planet's atmosphere. Neptune churns with the fastest winds in the solar system, reaching speeds of up to 1,200 miles per hour. This seems impossible for a world so far from the Sun that it receives only 1/10,000th of the sunlight that Earth does. The planet should be a frozen, quiet place, but instead it rages with storms and winds that dwarf anything we know on Earth. The energy for these incredible winds comes from within Neptune itself. The planet radiates 2.6 times more energy than it receives from the Sun, powered by heat left over from its formation and possibly by the slow gravitational compression of its interior. This internal furnace drives weather systems that can span continents, including the famous Great Dark Spot, a storm system the size of Jupiter's Great Red Spot that was first observed by Voyager 2 in 1989. But Neptune's storms are more dynamic than Jupiter's. When the Hubble Space Telescope looked at Neptune a few years later, the Great Dark Spot had vanished completely, replaced by new storm systems in different parts of the atmosphere. These storms appear and disappear like weather on a cosmic scale, reminding us that even the most distant worlds remain active and alive. Neptune's largest moon, Triton, orbits backwards around the planet, suggesting it was once a dwarf planet like Pluto that Neptune captured from the outer solar system. Triton is geologically active despite being so far from the Sun, with geysers of nitrogen erupting from its south pole and carrying dark material high into its thin atmosphere. These geysers create dark streaks across Triton's icy surface, like calligraphy written by cosmic winds. The dwarf planets of our outer solar system drift in peaceful exile beyond Neptune's orbit. Pluto, once considered the ninth planet, now leads a family of small worlds in the Kuiper Belt, each one a unique character in the solar system's extended family. These worlds are time capsules, preserving materials from the solar system's formation, largely unchanged for billions of years. Pluto and its largest moon, Charon, are locked in a gravitational dance, always showing the same face to each other as they orbit their common center of mass. They're so close in size that some astronomers consider them a double planet rather than a planet and moon. From Pluto's surface, Charon would appear 7 times larger than our moon appears from Earth, hanging motionless in Pluto's sky like a constant companion. The New Horizons spacecraft revealed that Pluto is far more complex and beautiful than anyone expected. Instead of a frozen, cratered wasteland, Pluto showed active geology with nitrogen glaciers, methane dunes, and a heart-shaped plain of smooth ice that has become one of the most beloved features in our solar system. The heart, informally named Tombaugh Regio after Pluto's discoverer, suggests that Pluto remains geologically active despite being smaller than Earth's moon and receiving virtually no energy from the distant Sun. Beyond Pluto lie even more mysterious worlds. Eris, slightly smaller than Pluto but more massive, tumbles through space in an orbit so elongated that it sometimes ventures 3 times farther from the Sun than Pluto. Makemake and Haumea spin in the darkness with their own moons and unique characteristics, each one a world we've barely begun to explore. Haumea spins so rapidly that it has stretched itself into an elongated shape, like a cosmic football tumbling end over end every 4 hours. It has its own ring system and 2 small moons, creating a miniature planetary system in the outer reaches of our solar neighborhood. These distant worlds remind us that our solar system extends far beyond the planets we learned about in school, stretching into regions where sunlight is so faint that noon resembles deep twilight on Earth. The Oort cloud surrounds our entire solar system like a vast, invisible shell of sleeping comets. This spherical cloud begins roughly 1,000 times farther from the Sun than Pluto and extends halfway to the nearest star. It contains perhaps 1 trillion icy bodies, each one a potential comet waiting for a gravitational nudge that might send it falling toward the inner solar system. These distant ice balls are the solar system's deep memory, preserving water and organic compounds from the nebula that gave birth to our sun and planets. Occasionally, the gravity of a passing star or the subtle influence of the galactic tide disturbs one of these frozen wanderers, sending it on a million-year journey toward the sun. As it approaches, solar heat begins to vaporize its surface, creating the glowing tail that makes comets some of the most beautiful visitors to our cosmic neighborhood. Most comets take thousands of years to complete their journeys, drifting through the outer darkness before swooping close to the sun in brilliant displays that last only months. Halley's Comet returns every 76 years like clockwork, its orbit so predictable that astronomers can trace its appearances back through history. Ancient Chinese astronomers recorded it in 240 BC, and it appeared over England in 1066, depicted in the Bayeux Tapestry as an omen before the Battle of Hastings. Each time a comet approaches the sun, it loses a little of itself. Solar radiation and the solar wind strip away layers of ice and dust, creating the magnificent tails that always point away from the sun, regardless of the comet's direction of travel. These tails can stretch millions of miles through space, so thin that Earth could pass through them without anyone on the surface noticing more than a gentle meteor shower. Eventually, after hundreds or thousands of passages, comets exhaust their volatile materials and fade into dark, rocky remnants. Some break apart entirely, creating streams of debris that Earth encounters annually, painting our skies with predictable meteor showers. The Perseids in August and the Geminids in December are cosmic gifts from comets that died long ago. Their final act, a gentle rain of light across our atmosphere. The asteroid belt between Mars and Jupiter contains the building blocks of a planet that never formed. Here, thousands of rocky bodies orbit the sun in a loose collection that science fiction often portrays as a treacherous obstacle course. In reality, the asteroids are spread so far apart that spacecraft routinely pass through the belt without coming close to any of them. The total mass of all the asteroids combined is less than 4% of our moon's mass. Ceres, the largest asteroid, is actually classified as a dwarf planet. Nearly 600 miles across, it contains about 1/3 of the asteroid belt's total mass and harbors surprising secrets. The Dawn spacecraft discovered that Ceres has a subsurface ocean of liquid water, kept warm by radioactive decay in its rocky core. Bright white deposits on its surface may be salt left behind when this hidden ocean occasionally breaches the surface and evaporates in the vacuum of space. Vesta, the second largest asteroid, bears the scars of ancient collisions that nearly shattered it completely. A massive impact billions of years ago created a crater so large it covers most of Vesta's southern hemisphere, blasting debris across the solar system. Some of these fragments eventually made their way to Earth as meteorites, allowing scientists to study pieces of Vesta in laboratories without ever leaving our planet. The asteroid belt marks a boundary in our solar system's architecture. Inside this realm lie the rocky terrestrial planets, warm worlds where metals and stone could condense from the solar nebula. Beyond it stretch the gas giants, massive worlds that formed where water and other compounds froze into ice, providing the solid material needed to build planetary cores massive enough to capture thick atmospheres of hydrogen and helium. Jupiter's gravitational influence prevented the asteroids from coalescing into a planet. The giant planet's gravity stirred the asteroid belt, causing collisions that shattered potential building blocks rather than allowing them to stick together. In this way, Jupiter acted as both protector and destroyer, preventing a fifth terrestrial planet from forming while also deflecting dangerous comets and asteroids away from the inner solar system. Some asteroids have become temporary companions to Earth, following horseshoe-shaped orbits that bring them close to our planet for decades or centuries before they drift away again. These quasi-satellites dance around Earth's orbital path without ever being captured as true moons, cosmic visitors that arrive and depart on schedules measured in geological time. The moons of our solar system tell stories of violence and beauty written in ice and stone. Europa, one of Jupiter's 4 largest moons, hides an ocean beneath its frozen surface that may contain twice as much water as all of Earth's oceans combined. The moon's icy shell cracks and shifts under Jupiter's gravitational pull, creating a constantly changing mosaic of ridges and valleys that suggests the hidden ocean below remains liquid and active. Enceladus, Saturn's small icy moon, surprised everyone when the Cassini spacecraft discovered geysers of water vapor erupting from its south pole. These fountains shoot hundreds of miles into space, fed by an underground ocean that may be in contact with the moon's rocky core. The interaction between water and rock could create the chemical conditions necessary for life, making Enceladus one of the most promising places to search for biology beyond Earth. Titan, Saturn's largest moon, is the only other world in our solar system with standing bodies of liquid on its surface. But instead of water, Titan's lakes and seas are filled with liquid methane and ethane, hydrocarbons that remain liquid in the moon's frigid environment. These alien seas experience weather patterns remarkably similar to Earth's water cycle, with methane rain falling from hydrocarbon clouds and carving river channels that flow toward the polar lakes. The atmosphere on Titan is thicker than Earth's, composed mostly of nitrogen with traces of methane that create an orange haze resembling smog. This thick atmosphere and low gravity would make Titan a paradise for flying. A person wearing simple wings could soar through Titan's skies like a bird, floating on air 4 times denser than Earth's, while weighing only 1/7 as much. Io, the innermost of Jupiter's large moons, experiences such intense gravitational flexing that it has turned inside out multiple times during its history. The moon's surface is constantly renewed by sulfur volcanism, creating a landscape painted in yellows, oranges, and reds like an abstract artwork. More than 400 active volcanoes dot Io's surface, some erupting with such violence that they throw material 300 miles above the surface, higher than the International Space Station orbits above Earth. Miranda, one of Uranus's moons, looks like it was assembled from spare parts. This small, icy world displays a patchwork of different terrains that seem to have no business being on the same object. Smooth plains adjoin regions of ridges and valleys, while massive cliff faces tower up to 12 miles high. Scientists believe Miranda may have been shattered by an ancient impact and then reassembled under its own gravity, creating a world that appears to have been broken and healed. Triton, Neptune's largest moon, orbits backwards around its planet while spewing dark geysers of nitrogen gas and dust up to 5 miles high. These eruptions are driven not by internal heat, but by the faint warmth of the distant sun, which manages to create enough pressure beneath Triton's translucent nitrogen ice to power these alien fountains. The geysers deposit dark streaks across Triton's surface, creating patterns that shift with the moon's slow seasons. Our solar system's magnetic fields create invisible sculptures in space, shaped by the solar wind and the rotation of worlds. Earth's magnetosphere forms a teardrop-shaped bubble around our planet, compressed on the side facing the sun and stretched into a long tail on the night side. This magnetic cocoon deflects most of the solar wind, but some particles leak through at the poles, creating the aurora that paint our skies in curtains of green, blue, and red light. Jupiter's magnetic field is 20,000 times stronger than Earth's, creating a magnetosphere so large that it would appear twice the size of the full moon in our sky if we could see it. This invisible giant traps radiation and charged particles, creating hazardous zones that can damage spacecraft electronics. The radiation belts around Jupiter are so intense that they would be lethal to humans, a reminder that the giant planet's beauty comes with hidden dangers. Mercury, despite being so close to the Sun, has its own modest magnetic field generated by its slowly cooling iron core. This field is only about 1% as strong as Earth's, but it's enough to deflect some of the solar wind and create tiny aurora near Mercury's poles, invisible to human eyes but detectable by spacecraft instruments. Mars once had a global magnetic field like Earth's, but it disappeared billions of years ago when the planet's core cooled and solidified. Without this protective shield, the solar wind gradually stripped away much of Mars's atmosphere, transforming it from a world that might have supported liquid water on its surface to the cold, dry desert we see today. Patches of magnetized rock in Mars's crust still remember the ancient field, creating a patchwork of local magnetic anomalies that tell the story of the planet's lost protection. The solar wind itself is a river of charged particles flowing outward from the sun at speeds of 1,000,000 miles per hour. This invisible stream carries the sun's magnetic field throughout the solar system, creating what scientists call the heliosphere, a bubble of solar influence that extends far beyond Pluto's orbit. At the edge of this bubble, the solar wind meets the interstellar medium, creating a boundary region where our solar system gradually transitions into the space between stars. The Voyager spacecraft have crossed this boundary, becoming the first human-made objects to enter interstellar space. They discovered that the heliosphere is not perfectly round, but is shaped more like a comet, compressed on one side by the direction of our solar system's motion through the galaxy and stretched into a tail on the other side. We are all passengers on a cosmic ship sailing through the Milky Way, protected by the sun's magnetic embrace. Gravity waves ripple through our solar system like invisible tides, stretching and compressing space itself as massive objects accelerate. These gravitational ripples, predicted by Einstein and finally detected in 2015, pass through our solar system constantly, carrying news of cosmic catastrophes from across the universe. Colliding black holes billions of light years away send their gravitational signals washing over Earth, causing the distance between particles to change by less than 1/10,000th the width of a proton. The planets themselves create tiny gravitational waves as they orbit the sun, though these are far too weak to detect with current instruments. But in principle, an alien civilization with sufficiently sensitive equipment could map our entire solar system just by listening to the gravitational music created by the dance of our worlds. Each planet contributes its own note to this cosmic symphony, from Mercury's rapid staccato to Neptune's deep, slow bass. Time itself flows differently throughout our solar system due to the effects of gravity and motion that Einstein revealed. Clocks run slightly slower on the surface of massive worlds like Jupiter than they do in the emptiness between planets. GPS satellites orbiting Earth must account for these relativistic effects, adjusting their clocks by microseconds each day to maintain accuracy. Without these corrections, navigation systems would drift off course by miles within hours. On the surface of the Sun, where gravity is 28 times stronger than Earth's, time passes more slowly than it does here. The difference is tiny, only about 2 parts in a billion, but it means that a clock on the Sun's surface would fall behind an identical clock on Earth by about 1 second every 16 years. These effects remind us that time is not the steady metronome we imagine, but a flexible dimension woven into the very fabric of space. The music of the spheres that ancient philosophers imagined turns out to be real, though not in the way they envisioned. Planets don't create audible sounds as they orbit, but they do generate radio waves, magnetic oscillations, and gravitational rhythms that can be translated into music. Saturn's radio emissions sound like haunting whale songs when converted to audio frequencies. Jupiter's magnetic field creates otherworldly tones as charged particles spiral around its field lines. Even Earth sings, generating electromagnetic waves in its magnetosphere that create an ethereal chorus, audible to sensitive radio receivers. These planetary songs change with the seasons, with solar activity, and with the complex gravitational interactions between worlds. The entire solar system participates in this hidden orchestra, each world contributing its voice to a cosmic composition that has been playing for billions of years, a soundtrack to the slow dance of planets that we are only beginning to learn how to hear. As we drift deeper into this cosmic lullaby, we find that our solar system is not the mechanical clockwork that earlier generations imagined, but a living, breathing, singing collection of worlds connected by invisible threads of gravity, magnetism, and time. Each planet, each moon, each asteroid and comet plays its part in a story larger than any single world could tell alone. The gentle facts continue to unfold like flower petals in the cosmic wind, each one a reminder that we live not on an isolated world, but as part of a neighborhood where ice dances, storms rage in slow motion, and gravity writes poetry in the orbits of distant worlds. The solar system cradles us in its vast embrace, a home both familiar and strange, both ancient and eternally young, spinning through the galaxy like a cosmic mobile hung in the nursery of space. The space between worlds holds its own quiet mysteries. What we call empty space is anything but empty, filled instead with the faintest whisper of particles, magnetic fields, and radiation that flows between planets like an invisible ocean. The solar wind carries with it the sun's breath, streaming outward at 1,000,000 miles per hour, yet so thin that it would be considered a perfect vacuum by Earth standards. This interplanetary medium shapes the paths of comets, bends the tails of solar wind, and carries messages between worlds in the form of charged particles and magnetic fluctuations. Spacecraft traveling between planets must navigate these invisible currents, sometimes using them like cosmic sails to adjust their trajectories. The space between Mars and Jupiter, once thought to be a void, actually contains enough dust and gas to create a faint zodiacal light visible from Earth just after sunset or before dawn. Even in the deepest reaches beyond Pluto, space hums with activity. Cosmic rays from distant stars thread through our solar system like invisible needles, carrying energy from supernovas that exploded millions of years ago. These high-energy particles interact with planetary atmospheres and magnetic fields, creating cascades of secondary particles that rain down gently onto every world in our cosmic neighborhood. The heliosphere, our solar system's protective bubble, extends roughly 4 times farther than Pluto's orbit before it meets the interstellar medium. At this boundary, called the heliopause, our sun's influence gradually fades into the space between stars. The Voyager probes discovered that this transition is not sharp, but gentle, like walking from a warm room into cool evening air, with properties of both regions mixing and blending across billions of miles. Temperature in space follows patterns that would seem backwards on Earth. While we think of outer regions as colder, the solar corona, the sun's outermost atmosphere, reaches temperatures of millions of degrees, even though it's farther from the nuclear furnace of the core than the sun's surface. This paradox occurs because the corona's particles are so spread out that despite their incredible speed, they carry very little total heat energy. Similarly, the upper atmospheres of planets can be surprisingly warm. Earth's thermosphere, where the International Space Station orbits, can reach temperatures of 3,600 degrees Fahrenheit during periods of high solar activity. Yet an astronaut working outside would still need heating systems because the air is so thin that these fast-moving molecules rarely collide with anything to transfer their energy. The dance of gravity creates resonances throughout our solar system, invisible connections that link the motions of distant worlds. Many of Jupiter's moons orbit in precise mathematical relationships with each other. For every 4 times Io orbits Jupiter, Europa completes exactly 2 orbits, and Ganymede completes exactly 1. This isn't coincidence, but the result of gravitational forces that have locked these moons into a cosmic harmony that has persisted for billions of years. Similar resonances appear throughout the solar system. Neptune and Pluto maintain a 3-to-2 resonance, with Neptune completing 3 orbits for every 2 of Pluto's. This gravitational partnership ensures that despite Pluto's highly elliptical orbit, the 2 worlds never come dangerously close to each other. Even when Pluto's path brings it closer to the Sun than Neptune, the resonance keeps them safely separated, like cosmic dancers who never step on each other's feet. The asteroid belt contains gaps called Kirkwood gaps where no asteroids are found. These empty zones correspond to orbital periods that would create resonances with Jupiter. Any asteroid that wandered into these regions would find its orbit gradually disturbed by Jupiter's repeated gravitational tugs, eventually being ejected from the belt entirely. The gaps are like gravitational no-man's lands, swept clean by Jupiter's invisible influence over millions of years. Tidal forces sculpt worlds throughout our solar system with patient artistry. On Earth, we notice tides in our oceans, but every solid body in space experiences tidal flexing as gravity pulls harder on the near side than the far side. This gentle stretching and squeezing generates heat through friction, powering geological activity on worlds that should be frozen solid. Io's spectacular volcanism is driven entirely by tidal heating from Jupiter's immense gravity. As Io orbits, it's stretched and compressed like a rubber ball, generating enough internal heat to keep its interior molten and power the most violent volcanic activity in the solar system. The moon essentially turns itself inside out every few million years, constantly resurfacing itself with fresh lava flows. Europa's hidden ocean stays liquid partly because of similar tidal heating. Jupiter's gravity flexes Europa's ice shell, cracking it into the beautiful patterns we see from space while generating enough heat to maintain a global ocean beneath the ice. This tidal energy may even drive circulation in Europa's ocean, creating currents and mixing that could support life in the dark waters far below the frozen surface. Even Earth's moon participates in this tidal dance. The same forces that raise our ocean tides gradually slow Earth's rotation and push the moon away from us. In Earth's early history, tidal forces from the much closer moon may have been strong enough to help mix the primordial oceans, stirring the chemical soup from which life eventually emerged. The colors of worlds tell stories written in chemistry and light. Mars appears red because iron in its soil has rusted over billions of years, oxidized by trace amounts of oxygen and water vapor in its thin atmosphere. This rusty dust is so fine that it stays suspended in the air during global dust storms, giving the entire planet a salmon-colored hue when viewed from space. Jupiter's bands of color come from different chemicals at different altitudes in its atmosphere. The pale zones are regions of rising gas where ammonia ice crystals form, while the darker belts are areas of descending gas where compounds have been altered by deeper heat and pressure. Traces of sulfur, phosphorus, and hydrocarbons create the subtle yellows, browns, and reds that paint Jupiter's cloud tops in ever-changing patterns. Uranus and Neptune appear blue because methane in their atmospheres absorbs red light and reflects blue wavelengths back to space. The deeper blue of Neptune compared to Uranus suggests that some additional component, perhaps organic compounds created by radiation, enhances the blue color in Neptune's atmosphere. These ice giants are like cosmic sapphires, their serene blue tones hiding violent winds and exotic forms of ice compressed into strange crystalline structures. Saturn's golden hue comes from a high-altitude haze of tiny particles, possibly hydrocarbons created when sunlight breaks apart methane molecules in the upper atmosphere. This gives the planet a warm, honey-colored appearance that contrasts beautifully with the brilliant white of its ice rings. The interplay between Saturn's golden clouds and silver rings creates one of the most aesthetically pleasing sights in our solar system. Even the sun changes color depending on how we observe it. In visible light, it appears white with a slight yellow tinge. In ultraviolet, it blazes with invisible fire. In X-ray wavelengths, it reveals a dynamic corona writhing with magnetic field lines and solar flares. Each wavelength of light tells a different story about our star's complex, layered atmosphere and the nuclear fusion reactions that power its gentle fire. The moons of our solar system display an artist's palette of colors and textures. Io appears yellow and orange from sulfur compounds ejected by its volcanoes. Europa gleams white and blue, its ice surface marked by dark streaks that may be organic compounds from its hidden ocean. Ganymede shows patches of dark, ancient terrain mixed with younger, brighter regions where impacts have exposed fresh ice. Enceladus shines like a perfect white pearl, its surface so reflective that it bounces back nearly all the sunlight that hits it. This high reflectivity, combined with its small size, keeps Enceladus incredibly cold despite its geological activity. The contrast between its frigid surface and warm interior creates the conditions necessary for its spectacular water geysers. Titan appears orange through the haze of its thick atmosphere, but beneath those clouds lies a world of surprising diversity. Liquid methane lakes appear dark against brighter continents of water, ice, and organic compounds. Sand dunes made of hydrocarbon particles march across Titan's equatorial regions, sculpted by winds that blow at only a few miles per hour but persist for months at a time in the moon's thick air. The phases of worlds beyond Earth create their own celestial rhythms. Mars shows phases like the moon when viewed from Earth, appearing gibbous when it's on the far side of the sun and nearly full when it's closest to us. Venus displays the most dramatic phases, appearing as a brilliant morning or evening star that waxes and wanes like the moon, but much more slowly, taking months to cycle through its phases as it orbits between Earth and the sun. From Mars, Earth and the Moon appear as a double star, sometimes close together, sometimes separated depending on the Moon's position in its orbit. Earth would show phases to a Martian observer, appearing as a brilliant blue crescent when Mars and Earth are on the same side of the Sun. The Moon would appear as a much fainter companion, occasionally passing in front of Earth to create a transit visible to any Martian astronomers who might be watching. Jupiter's moons create their own complex dance of phases, eclipses, and transits as viewed from the giant planet. Io, Europa, Ganymede, and Callisto regularly pass behind Jupiter, disappear into its shadow, or cast their own shadows onto the planet's cloud tops. These events occur with clockwork precision, allowing astronomers to map the orbits of Jupiter's moons with extraordinary accuracy. The seasons on tilted worlds create patterns of light and shadow that would seem alien to Earth dwellers. On Uranus, each pole experiences 42 years of continuous sunlight, followed by 42 years of darkness. During the planet's long summer, one hemisphere basks in eternal day, while the other freezes in perpetual night. The transition between seasons happens gradually over years as the planet's strange orientation slowly changes which regions receive sunlight. Mars experiences dust devil seasons when temperature differences create thousands of small whirlwinds that march across the planet's surface. These dust devils are much larger than their Earth counterparts, some towering 12 miles high, but they're also much gentler due to Mars' thin atmosphere. From orbit, they appear as dark tracks crisscrossing the planet's surface, temporary signatures of the Martian atmosphere's restless energy. On Titan, the seasons bring methane rain to different hemispheres. Currently, it's late spring in Titan's northern hemisphere, where the largest lakes are filling with liquid hydrocarbons from seasonal precipitation. In about 15 years, as Saturn's orbit carries Titan into its northern summer, these patterns will reverse, and the northern lakes may begin to evaporate while southern regions receive more rainfall. The rotation periods of worlds create days of wildly different lengths throughout our solar system. A day on Venus lasts 243 Earth days, longer than Venus's 225-day year. This means the sun rises in the west on Venus and takes 4 months to cross the sky before setting in the east. The slow rotation may be due to atmospheric tides raised by the sun, which gradually slowed Venus's spin over billions of years. Mercury's day is exactly 2/3 as long as its year due to a gravitational resonance with the sun. This means Mercury rotates exactly 3 times for every 2 orbits, creating a complex pattern where some parts of the planet experience double sunrises and sunsets. From certain locations on Mercury, the sun would appear to rise, stop, move backward, then move forward again before setting, all due to the interplay between the planet's orbital motion and rotation. Jupiter spins so fast that its day lasts only 9 hours and 56 minutes, despite being 11 times wider than Earth. This rapid rotation flattens the giant planet noticeably, making it wider at its equator than from pole to pole. The fast spin also helps drive Jupiter's powerful magnetic field and contributes to the banded structure of its atmosphere, as the Coriolis force organizes the planet's weather systems into east-west flowing streams. Gas giant storms persist for decades or centuries because there's no solid surface to slow them down through friction. On Earth, hurricanes weaken rapidly when they move over land, but on Jupiter, Saturn, Uranus, and Neptune, storms can maintain their strength for hundreds of years, fed by heat from the planet's interior and unimpeded by continents or mountains. The hexagonal storm at Saturn's North Pole is one of the most geometrically perfect features in the solar system. This six-sided jet stream is wider than two Earths and has maintained its shape for decades. The hexagon forms because of the precise balance between the storm's rotation speed and the planet's atmospheric dynamics, creating standing waves that naturally organize into this striking geometric pattern. Neptune's Great Dark Spot, discovered by Voyager 2, was a storm system comparable in size to Jupiter's Great Red Spot. But when the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had vanished completely, replaced by new storm systems elsewhere on the planet. This demonstrates that while gas giant storms can be long-lived, they're not necessarily permanent features like the continents and oceans of terrestrial worlds. Atmospheric escape shapes the evolution of planetary atmospheres over geological time. Light gases like hydrogen and helium move fast enough to escape from smaller worlds, which is why Earth and Mars have lost most of their primordial atmospheres, while the gas giants have retained theirs. Mars continues to lose atmosphere today, with the solar wind gradually stripping away its thin air at a rate of about 100 grams per second. Venus may have once had oceans, but a runaway greenhouse effect boiled them away, and the water vapor was broken apart by solar radiation. The hydrogen escaped to space while the oxygen combined with surface rocks, leaving Venus with its current thick atmosphere of carbon dioxide and sulfuric acid clouds. This process took hundreds of millions of years, transforming what might once have been an Earth-like world into the furnace planet we see today. Even Earth loses atmosphere, though at a much slower rate than Mars. Our planet's magnetic field protects us from the worst effects of the solar wind, but we still lose about 90 tons of atmosphere to space every day. This sounds like a lot, but it's negligible compared to the total mass of our atmosphere. At this rate, it would take trillions of years to lose a significant fraction of our air. The ice and snow of outer solar system worlds create landscapes unlike anything on Earth. On Pluto, methane snow falls from thin clouds and accumulates in drifts that are gradually redistributed by the dwarf planet's faint winds. The snow appears blue to human eyes because methane ice absorbs red light more strongly than blue, creating an alien winter wonderland lit by sunlight 1,000 times dimmer than Earth receives. Triton's geysers create dark streaks across its south polar region, where nitrogen geysers carry carbonaceous material up to 5 miles above the surface before depositing it downwind. These streaks change with Triton seasons, which last decades due to Neptune's long orbital period. The geysers are powered by the faint warmth of the distant sun, which manages to create enough pressure beneath Triton's translucent nitrogen ice cap to drive these spectacular eruptions. Europa's ice shell may be 15 to 25 miles thick, floating on an ocean that could be 60 miles deep. The surface shows evidence of recent geological activity, with smooth regions where the ice has been resurfaced and chaotic terrain where the crust has been broken up and refrozen. Some areas show what appear to be icebergs, chunks of the surface that have broken off and rotated before freezing back into place. Enceladus creates its own snow by ejecting water vapor from its south polar geysers. Some of this material falls back to the surface as ice particles, while the rest escapes to form Saturn's E ring, a faint ring of microscopic ice crystals that extends from inside Enceladus's orbit to well beyond it. In this way, Enceladus is gradually dispersing its interior into space, creating a ring from its own substance. The magnetic fields of worlds create invisible sculptures that extend far into space. Earth's magnetosphere has a long tail that stretches beyond the Moon's orbit, twisted by the solar wind into a helical structure that rotates with our planet. During periods of high solar activity, this magnetic tail can store energy and then release it suddenly, sending waves of charged particles back toward Earth to create auroras. Jupiter's magnetosphere is so large that it would appear 5 times the size of the full moon in Earth's sky if we could see it. This enormous magnetic bubble traps radiation and creates some of the most intense radiation environments in the solar system. The radiation belts around Jupiter are so dangerous that spacecraft must be specially shielded to survive passing through them, and some of Jupiter's moons are constantly bathed in radiation levels that would be lethal to life as we know it. Saturn's magnetic field creates a unique structure because it's almost perfectly aligned with the planet's rotation axis, unlike every other planet in the solar system. This creates a nearly symmetrical magnetosphere without the wobbles and variations seen around other worlds. The magnetic field also interacts with Saturn's rings and moons in complex ways, creating spokes in the rings and auroras on some of the moons. The solar system's architecture reveals the story of its formation, written in the orbits and compositions of its worlds. The inner rocky planets formed where it was hot enough for metals and silicates to condense from the solar nebula. The asteroid belt marks the boundary where water began to freeze, providing the solid material needed to build larger worlds. Beyond this frost line, the gas giants accumulated massive cores of rock and ice that captured thick atmospheres of hydrogen and helium. The spacing of planetary orbits follows a rough pattern known as the Titius-Bode law, though it's more of a curious coincidence than a fundamental principle. Each planet's orbit is roughly twice as far from the Sun as the previous one, with some exceptions. This pattern may reflect the way gravitational resonances organized the early solar system, with each forming planet sweeping its orbital zone clear of debris. The late heavy bombardment, a period of intense asteroid and comet impacts that ended about 3.8 billion years ago, shaped the surfaces of worlds throughout the inner solar system. The Moon's heavily cratered highlands preserve a record of this ancient violence, while Earth's active geology has erased most traces of this early battering. Mars and Mercury still bear the scars of this bombardment in their ancient, crater-covered terrains. Migration of the giant planets early in solar system history may have triggered the late heavy bombardment. As Jupiter and Saturn moved inward and then outward again, their gravitational influence scattered asteroids and comets throughout the solar system, sending a shower of debris toward the inner planets. This grand tack migration also explains some puzzling features of our solar system, such as why Mars is smaller than expected and why the asteroid belt contains so little mass. The Kuiper belt beyond Neptune contains the leftover building blocks of the outer solar system, preserved in cold storage for billions of years. These objects are like cosmic time capsules containing pristine materials from the solar nebula that have remained largely unchanged since the planets formed. Studying Kuiper belt objects gives us insights into the conditions and processes that shaped our cosmic neighborhood during its earliest days. Scattered disk objects follow highly elliptical orbits that take them far beyond the Kuiper belt before bringing them back closer to the Sun. These distant wanderers may be the source of long-period comets, nudged by gravitational interactions into orbits that carry them into the inner solar system where they blaze briefly as comets before returning to the outer darkness. The heliopause, where our solar system meets interstellar space, is not a fixed boundary, but a dynamic region that expands and contracts with the solar cycle. During periods of high solar activity, the heliosphere swells outward as the strengthened solar wind pushes against the interstellar medium. During solar minimum, this boundary contracts inward, allowing more cosmic rays from deep space to penetrate into our solar system. Voyager 1 and 2 have crossed this boundary and entered the interstellar medium, becoming humanity's first ambassadors to the space between stars. They've discovered that interstellar space is not empty, but filled with a thin plasma of charged particles and threaded with magnetic fields that carry information about nearby stars and the structure of our local galactic neighborhood. The solar system moves through the galaxy at 514,000 miles per hour, carrying all its worlds on a grand journey around the Milky Way's center. This galactic year lasts about 225 million Earth years, meaning our solar system has completed only about 20 orbits since it formed. During this cosmic journey, we encounter different regions of the galaxy, sometimes passing through the spiral arms where star formation is active, sometimes drifting through quieter regions between the arms. Our current location in the Orion arm of the Milky Way is relatively peaceful, with few nearby supernovas or other violent events that could disrupt life on Earth. But over geological time, our solar system's galactic orbit carries us through regions of varying density and activity, potentially influencing the rate of comet impacts and cosmic ray exposure that Earth experiences. The solar system breathes with a rhythm set by the Sun's magnetic field, which reverses polarity every 11 years as part of the solar cycle. This creates a 22-year pattern in the heliosphere as the Sun's magnetic field lines spiral outward through the solar wind, alternately focusing and defocusing cosmic rays that try to enter our solar system from interstellar space. These cosmic rhythms connect our small corner of the universe to the larger galaxy, reminding us that our solar system is not an isolated island but part of a vast community of stars, all orbiting the galaxy's center in a stately cosmic dance that has continued for billions of years and will continue for billions more. The gentle facts continue to unfold like ripples in a cosmic pond, each one revealing new connections between the worlds that share our stellar neighborhood, from the quantum fluctuations in empty space to the vast magnetic fields that embrace entire planets. Our solar system reveals itself as a place of infinite subtlety and grace, where every world tells its own story while participating in the larger symphony of gravitational, magnetic, and radiative forces that bind us all together in one harmonious whole. As we continue our gentle drift through space, we find ourselves drawn to the quieter mysteries that exist in the spaces between understanding. The solar system holds secrets that whisper rather than shout, phenomena that unfold over timescales so vast they seem almost eternal, yet so precise they reveal the hidden clockwork of the cosmos. The solar wind carries with it a kind of cosmic memory, particles that left the sun's surface days or weeks ago finally reaching the outer planets to interact with their magnetic fields and atmospheres. This stellar breath creates a connection between all worlds, a shared atmosphere of sorts that extends throughout our solar neighborhood. When solar storms erupt from our star's surface, their effects ripple outward like waves in a pond, eventually reaching every planet, moon, and asteroid in their path. These solar particles, mostly protons and electrons moving at incredible speeds, carry with them the electromagnetic signature of the sun's magnetic field. As they encounter planetary magnetic fields, they create invisible light shows in the form of radio emissions that can be detected by sensitive instruments. Jupiter's radio storms, triggered by solar wind interactions, can be heard on Earth with simple radio equipment, sounding like ocean waves breaking on a distant shore. The gravitational influence of worlds extends far beyond what we might imagine. Earth's gravity creates tiny but measurable effects on spacecraft passing by other planets. When Voyager 2 flew past Neptune in 1989, its radio signals revealed minute changes in the probe's velocity caused by gravitational waves propagating through the solar system. These ripples in space-time, created by the orbital dance of distant binary stars, pass through our solar neighborhood constantly, carrying messages from cosmic events we can barely comprehend. Even more subtly, the planets influence each other's orbits in ways that accumulate over millions of years. Computer simulations show that the solar system's configuration is delicately balanced, with the possibility that Mercury's orbit could become unstable in about 5 billion years, due to the accumulated gravitational tugs from Venus and Jupiter. Such is the precision of celestial mechanics that events separated by billions of years are connected by invisible threads of gravitational influence. The surfaces of worlds tell stories of cosmic weather written in stone and ice. On Mars, the patterns of sand dunes reveal the planet's ancient climate history, with different layers showing how wind patterns have changed over millions of years. Some dunes appear to be actively moving today, shifting grain by grain in the thin Martian air, while others have been locked in place for eons, preserved like fossils of ancient weather systems. Venus shows evidence of global climate catastrophes that resurfaced the entire planet relatively recently in geological terms. The surface appears to be only 500 million years old, suggesting that the planet underwent a complete renewal that erased all traces of its earlier history. Whether this happened gradually through volcanism or suddenly through some unknown process remains one of Venus's most intriguing mysteries. The ice caps on Mars grow and shrink with the seasons, but they also show longer-term cycles that may be driven by changes in the planet's orbital tilt and eccentricity. These Milankovitch cycles, similar to those that drive ice ages on Earth, create climate patterns on Mars that span hundreds of thousands of years. Some scientists believe Mars may currently be emerging from an ice age, with water vapor slowly being released from polar ice deposits back into the atmosphere. The sounds of space, though transmitted through electromagnetic waves rather than air, create an otherworldly symphony that reveals the hidden activity of seemingly quiet worlds. Saturn's rings generate radio waves as tiny particles collide and exchange electrical charge, creating a constant whisper of static that changes in pitch and intensity with the planet's rotation. These ring sounds are most active during Saturn's equinoxes, when sunlight strikes the ring edges and creates more electrical activity. Jupiter's moon. Io creates its own radio emissions through the interaction of its volcanic gases with Jupiter's powerful magnetic field. As Io orbits through this magnetic environment, it generates electrical currents strong enough to link it electrically to Jupiter's upper atmosphere, creating a kind of cosmic wire that carries 1,000,000 amperes of current between the moon and planet. Even Earth contributes to this cosmic chorus through the interaction of our magnetosphere with the solar wind. The bow shock, where the solar wind first encounters Earth's magnetic field, generates waves that sound like haunting melodies when converted to audio frequencies. These Earth songs change with solar activity, becoming more intense during geomagnetic storms and quieter during periods of calm space weather. The Chemistry of Worlds reveals the story of stellar alchemy written in the very atoms that compose planets and moons. Every element heavier than hydrogen and helium was forged in the nuclear furnaces of ancient stars, then scattered into space when those stars died. The iron in Earth's core, the oxygen in our atmosphere, the calcium in our bones, all were created billions of years ago in stellar explosions that seeded the galaxy with the building blocks of worlds. Different types of meteorites preserve samples of this ancient stellar material, allowing us to study the composition of the solar nebula from which our planets formed. Some meteorites contain tiny diamonds that formed in the shock waves of supernovas, microscopic gems that are older than our solar system and carry within their crystal structure the memory of stellar death and rebirth. The isotopic composition of noble gases in planetary atmospheres tells the story of each world's formation and evolution. Mars shows evidence of having lost most of its original atmosphere to space, with the remaining gases enriched in heavier isotopes that were less likely to escape. Venus's atmosphere contains isotopic ratios that suggest its water was lost through a runaway greenhouse effect, with hydrogen escaping to space and leaving behind a thick atmosphere of carbon dioxide. The moons of the outer planets preserve in their icy shells a record of the solar system's bombardment history. Europa's surface, constantly renewed by geological activity, shows relatively few impact craters, suggesting active resurfacing within the last few million years. In contrast, Callisto's ancient, heavily cratered surface has remained unchanged for billions of years, preserving a record of the late heavy bombardment that shaped the early solar system. The organic chemistry found throughout the solar system hints at processes that may be common wherever the right conditions exist. Titan's thick atmosphere produces complex hydrocarbon molecules that rain down onto the surface, creating a chemical environment that may resemble early Earth before life began. The discovery of amino acids in meteorites and organic compounds in comets suggests that the building blocks of life are widespread throughout our cosmic neighborhood. Enceladus's water geysers contain not only water vapor but also organic molecules, hydrogen gas, and other compounds that could potentially support microbial life. The chemistry detected in these plumes suggests that Enceladus's ocean may be in contact with its rocky core, allowing water-rock interactions that could create the chemical energy needed to drive biological processes. The magnetic fields of worlds create invisible weather systems that extend far into space. Earth's magnetosphere experiences storms when solar wind conditions change, with charged particles accelerating to high energies and creating radiation belts that can be dangerous to spacecraft and astronauts. These magnetic storms can last for days, gradually subsiding as the solar wind conditions a sphere is so large and dynamic that it experiences return to normal. Jupiter's magnet weather patterns that dwarf anything seen on planetary surfaces. Magnetic storms on Jupiter can release more energy than the most powerful earthquakes on Earth, sending shock waves through the giant planet's magnetic field that can be detected by spacecraft millions of miles away. The interaction between solar wind and planetary magnetic fields creates current systems that flow through space like invisible rivers. These currents, composed of charged particles following magnetic field lines, connect different regions of a planet's magnetosphere and can transport energy and particles across vast distances. On Earth, these currents contribute to the aurora by carrying particles from the magnetosphere's tail region back toward the polar atmosphere. The tidal forces that shape moons and planets work on timescales that span the entire history of the solar system. The moon's current distance from Earth represents a balance between the tidal forces that are pushing it away and other gravitational influences that tend to bring it back. This delicate balance has been evolving for billions of years and will continue to evolve for billions more. Io's tidal heating is so intense that the moon's interior may be completely molten except for a thin crust at the surface. This makes Io essentially a ball of liquid rock with a solid skin, constantly flexed and kneaded by Jupiter's gravity. The energy dissipated by this tidal heating is equivalent to about 100,000 nuclear power plants running continuously. Europa's ice shell flexes by up to 100 feet twice during each orbit around Jupiter, creating cracks and ridges that record the moon's tidal history. These tidal stresses may also help mix Europa's ocean by driving convection currents that could bring nutrients from the rocky seafloor to regions closer to the ice-water boundary. The resonances that lock moons into precise orbital relationships create a kind of cosmic music, with each moon contributing its gravitational influence to maintain the overall harmony. The Galilean moons of Jupiter have maintained their resonant relationship for billions of years, with each orbit precisely timed to reinforce the stability of the entire system. Similar resonances exist throughout the solar system, from the asteroid belt's Kirkwood gaps to the precise relationship between Neptune and Pluto. These gravitational partnerships demonstrate how the solar system has organized itself into stable configurations that can persist for geological ages, each world finding its place in the cosmic dance through the patient work of gravity over millions of years. The rotation of worlds creates internal dynamics that drive geological activity and atmospheric circulation. Earth's rotation generates the Coriolis force that organizes our weather into the familiar patterns of high and low pressure systems. The same force operates on other worlds, creating banded atmospheric structures on the gas giants and influencing the circulation patterns in the atmospheres of Venus and Mars. The rapid rotation of gas giants creates equatorial bulges that affect their gravitational fields and influence the orbits of their moons. Jupiter's oblate shape, flattened by its 10-hour rotation period, creates gravitational harmonics that can be detected by spacecraft and used to study the planet's interior structure. Venus's incredibly slow rotation creates atmospheric dynamics unlike anywhere else in the solar system. Without the Coriolis force to organize weather patterns, Venus's thick atmosphere circulates in simple cells that carry heat from the day side to the night side, maintaining nearly uniform temperatures across the entire planet despite its extremely long day-night cycle. The seasonal cycles of worlds create rhythms that span years or decades, yet follow patterns as predictable as Earth's annual seasons. Mars experiences global dust storm seasons that occur roughly every 2 Martian years, triggered by temperature differences that become extreme during the planet's closest approach to the Sun. These storms can last for months and affect weather patterns across the entire planet. Saturn's seasonal changes are subtle but measurable, with temperatures in different parts of the atmosphere rising and falling as the planet's 29-year orbit carries it through its solar year. The hexagonal storm at Saturn's North Pole shows seasonal variations in its structure and intensity, demonstrating that even the most stable atmospheric features respond to the changing seasons. Uranus's extreme seasons create temperature differences between hemispheres that persist for decades. Currently, the planet's south pole is experiencing summer after 42 years of continuous sunlight, while the North Pole is slowly emerging from an equally long winter. The transition between these extreme seasons happens gradually, creating atmospheric circulation patterns that are still being studied by planetary scientists. The light from our sun takes different amounts of time to reach each world, creating a subtle hierarchy of illumination that connects all the planets. Sunlight reaches Mercury in just over 3 minutes, while the same photons take more than 4 hours to reach Neptune. This means that when we observe the outer planets, we're seeing them illuminated by sunlight that left the sun hours earlier, creating a temporal depth to our solar system observations. The inverse square law ensures that each world receives a different amount of solar energy, creating the temperature gradients that drive atmospheric circulation and seasonal changes. Mars receives only 43% as much sunlight per square meter as Earth, while Jupiter receives only 4% and Neptune receives just 0.1%. These differences in solar heating create the diverse climate systems we observe throughout the solar system. The albedo, or reflectivity, of different worlds determines how much of this solar energy they absorb versus reflect back to space. Ice-covered moons like Enceladus reflect almost all the sunlight they receive, staying incredibly cold despite their geological activity. Dark objects like asteroids and comets absorb most of the sunlight, warming enough to drive sublimation processes that create their characteristic tails and atmospheres. The greenhouse effects on different worlds demonstrate how atmospheres can amplify or moderate the influence of solar heating. Venus's thick carbon dioxide atmosphere creates a runaway greenhouse effect that makes the planet hotter than Mercury, despite being farther from the Sun. Mars's thin atmosphere provides almost no greenhouse warming, allowing surface temperatures to plunge far below freezing even at the equator. Earth's greenhouse effect is perfectly tuned to maintain liquid water on the surface, creating the temperate conditions that have allowed life to flourish for billions of years. This delicate balance depends on the precise composition of our atmosphere and the complex interactions between oceans, ice, and atmospheric circulation that regulate our planet's temperature. The escape of atmospheres from planets happens through several different mechanisms, each operating on different timescales and affecting different atmospheric components. Thermal escape allows the lightest gases to reach velocities high enough to overcome planetary gravity, which is why hydrogen and helium are rare in the atmospheres of terrestrial planets. Solar wind sputtering can strip away heavier gases from planets without strong magnetic fields, gradually eroding atmospheres over billions of years. Mars has lost much of its original atmosphere through this process, with the solar wind continuously removing particles from the top of the Martian atmosphere and carrying them away into interplanetary space. Impact erosion, caused by large asteroid or comet impacts, can blast away significant portions of an atmosphere in single events. Early in solar system history, when impacts were more frequent and more violent, this process may have been responsible for major atmospheric losses on terrestrial planets, potentially explaining why Mars has such a thin atmosphere today. The hydrodynamic escape that may have affected early Earth and Venus involves the entire upper atmosphere expanding and flowing away into space, driven by extreme heating from the young sun or from massive impacts. This process could have removed hydrogen-rich atmospheres from terrestrial planets early in their histories, leaving behind the oxidized atmospheres we observe today. The magnetic fields generated by planetary cores create protective bubbles that help preserve atmospheres over geological time. Earth's magnetic field deflects most of the solar wind around our planet, limiting atmospheric loss to a manageable rate that allows our atmosphere to persist for billions of years. The loss of Mars's global magnetic field about 4 billion years ago may have been the key event that allowed the solar wind to begin stripping away the planet's atmosphere. Without magnetic protection, Mars became vulnerable to atmospheric erosion that gradually transformed it from a potentially habitable world to the cold, dry planet we see today. The generation of planetary magnetic fields depends on the presence of liquid, electrically conducting cores that can sustain convection currents. Earth's magnetic field is powered by convection in our liquid iron outer core, driven by heat from radioactive decay, and the gradual cooling and solidification of the inner core. Mercury's weak magnetic field suggests that its iron core is still partially liquid despite the planet's small size. The survival of this magnetic field may be due to Mercury's large iron core, which makes up about 75% of the planet's radius and provides enough thermal energy to maintain core convection. Venus lacks a magnetic field despite being similar in size to Earth, possibly because its slow rotation prevents the formation of the convection patterns needed to generate a magnetic dynamo. The absence of a magnetic field may have contributed to Venus's atmospheric evolution, allowing the solar wind to influence atmospheric chemistry and escape processes. The gas giants generate their magnetic fields through convection in layers of metallic hydrogen deep within their interiors. These magnetic fields are much stronger than those of terrestrial planets and create complex magnetospheres that interact with their many moons and ring systems. The auroras that result from magnetic field interactions create some of the most beautiful phenomena in the solar system. Earth's aurora are powered by solar wind particles that follow magnetic field lines down into the polar atmosphere, where they collide with gas molecules and create the familiar green and red curtains of light. Jupiter's auroras are powered not only by solar wind interactions, but also by particles from its volcanic moon Io, which creates a plasma torus around Jupiter that feeds the planet's radiation belts. These auroras are much more intense than Earth's and extend into ultraviolet and X-ray wavelengths that are invisible to human eyes, but detectable by space telescopes. Saturn's auroras show unique patterns related to the planet's ring system and its many moons. Some of Saturn's auroras appear to be connected to specific moons, with bright spots in the aurora corresponding to the orbital positions of moons like Enceladus and Dione. The radio emissions generated by these magnetic interactions create a kind of interplanetary radio network, with each magnetized world broadcasting its own characteristic signals into space. These radio signatures can be detected from great distances and provide information about magnetic field strength, rotation periods, and the presence of moons or rings. As our gentle journey through the solar system continues, we discover that every world participates in processes that connect them across the vast distances of space. From the solar wind that touches every planet to the gravitational resonances that link distant moons, our cosmic neighborhood reveals itself as an interconnected system where every component influences every other component in subtle but profound ways. The beauty of these connections lies not in their complexity, but in their simplicity. The same physical laws that govern the motion of planets also determine the behavior of atoms in our bodies. The same forces that create aurora on distant worlds also shape the magnetic field that protects our own planet. In understanding our solar system, we discover not just a collection of separate worlds, but a unified system of extraordinary elegance and grace, spinning together through space in a cosmic dance that has continued for billions of years and will continue for billions more. The chemistry of comets reveals recipes written in the earliest days of our solar system. These dirty snowballs carry within their frozen hearts the same water, carbon compounds, and organic molecules that may have seeded Earth with the ingredients for life. When comets warm as they approach the sun, they release not just water vapor, but complex organic molecules, amino acids, and even simple sugars, creating a cosmic chemistry set that has remained largely unchanged for 4.5 billion years. Each comet is unique, carrying a slightly different mixture of ices and dust that reflects the region of the solar nebula where it formed. Comets from the Kuiper belt tend to be richer in carbon monoxide and methane, while those from the distant Oort cloud often contain more water ice and complex organic compounds. This chemical diversity suggests that the early solar system was not uniform but contained distinct regions with different temperatures and compositions. The dust released by comets as they sublime creates some of the most delicate structures in space. These microscopic particles, no larger than cigarette smoke, spread out along the comet's orbit to form streams that Earth encounters annually as meteor showers. When these tiny fragments enter our atmosphere at speeds of up to 160,000 miles per hour, they create the brief streaks of light we call shooting stars, each one a messenger from the outer reaches of our solar system. Some comet dust is so fine that it can be carried by solar radiation pressure and the solar wind, spreading throughout the inner solar system to create the zodiacal light, a faint pyramid of light visible just after sunset or before dawn. This phenomenon represents sunlight reflecting off countless microscopic comet particles distributed throughout the plane of our solar system, creating a gentle reminder of the cosmic dust that surrounds us. The nucleus of a comet, hidden beneath its glowing coma and streaming tails, is often described as a dirty snowball, but spacecraft visits have revealed structures more complex and beautiful than anyone imagined. Comet nuclei are not smooth spheres, but irregular, porous bodies with cliffs, valleys, and jets that erupt from specific locations as solar heating reaches pockets of volatile material beneath the surface. The Rosetta mission to Comet 67P revealed a world in miniature, complete with seasonal changes, weather patterns driven by sublimation, and even a day-night cycle that affects which jets are active. The comet's surface showed signs of erosion and change, with cliffs collapsing and new features appearing as the nucleus shed layers of material during its passage around the Sun. The gravity on a comet nucleus is so weak that a person could easily leap from one side to the other, and walking would be impossible without magnetic boots or some other anchoring system. The escape velocity from most comets is only a few miles per hour, slower than a gentle jog on Earth. This makes comet nuclei incredibly fragile environments where even small disturbances can launch material into space. The formation of comet tails follows patterns as predictable as the phases of the Moon, yet each tail is unique in its structure and behavior. As a comet approaches the Sun, solar radiation begins to warm its surface, creating jets of gas and dust that initially form a spherical coma around the nucleus. The solar wind then sweeps this material away from the Sun, creating the characteristic tails that can stretch millions of miles through space. Most comets develop two distinct tails as they near the Sun. The dust tail, composed of heavier particles, follows a curved path as it's pushed away by solar radiation pressure, while the ion tail, made of charged gas molecules, points straight away from the Sun as it's carried by the solar wind. These twin tails create some of the most photogenic objects in the solar system, ethereal streamers that appear and disappear with each comet's journey. The interaction between comet tails and Earth's atmosphere creates meteor showers that follow annual schedules as predictable as the calendar. When Earth passes through the debris stream left by a comet, we experience increased meteor activity as these ancient particles burn up in our atmosphere. The Perseid meteor shower in August comes from comet Swift-Tuttle, while the Geminids in December originate from an asteroid-like object that may be the rocky remains of an extinct comet. Some meteor showers produce fireballs bright enough to cast shadows and leave glowing trains that persist for minutes, visible reminders of the high-energy collisions between comet particles and Earth's atmosphere. These events connect us directly to the outer solar system, bringing samples of distant worlds literally to our doorstep in the form of microscopic dust that settles gently to Earth's surface. The long-period comets that visit our inner solar system carry with them the gravitational signatures of their journeys through the Oort cloud. Some show evidence of close encounters with other stars, their orbits perturbed by stellar gravity during our solar system's travels through the galaxy. These cosmic wanderers are messengers not just from the edge of our solar system, but from the interstellar medium beyond. The discovery of interstellar objects passing through our solar system has revealed that comets and asteroids regularly travel between star systems, carrying with them samples of alien worlds. Oumuamua, the first confirmed interstellar visitor, showed properties unlike any comet or asteroid from our own solar system, suggesting that other star systems produce objects with different compositions and structures than our own. These interstellar visitors spend only months in our solar system before continuing their journeys to other stars, but their brief visits provide glimpses into the planetary systems of distant suns. Future missions may attempt to intercept such objects, giving us our first direct samples of material from other star systems without the need for interstellar travel. The asteroid families scattered throughout the main belt tell stories of ancient collisions written in the orbital mechanics of thousands of fragments. When a large asteroid suffers a catastrophic impact, the resulting debris spreads out along similar orbits, creating groups of asteroids with related compositions and trajectories. These families can be traced back to specific collision events that occurred millions of years ago. The Vesta family includes thousands of asteroids that were blasted from the surface of the asteroid Vesta by a massive impact that created the enormous crater visible on Vesta's south pole today. Some of these fragments have made their way to Earth as meteorites, allowing scientists to study pieces of Vesta in terrestrial laboratories and compare them with observations from spacecraft visiting the asteroid itself. The study of asteroid families reveals that the asteroid belt was once much more densely populated than it is today. Collisions have been grinding down the asteroid population for billions of years, creating the size distribution we observe today, with many small fragments for every large body. This collisional evolution continues today, though at a much slower rate than in the early solar system. The Trojan asteroids that share Jupiter's orbit demonstrate the subtle gravitational architecture that organizes our solar system. These asteroids cluster at 2 points along Jupiter's orbital path, 60 degrees ahead of and behind the giant planet, where the combined gravity of the Sun and Jupiter creates stable zones known as Lagrange points. Here, small bodies can remain in stable orbits for billions of years, protected by the gravitational balance between the two massive bodies. Similar Trojan populations exist at the Lagrange points of other planets, including Earth, Mars, and Neptune. These gravitational harbors provide safe havens where asteroids and dust can accumulate, creating natural laboratories for studying the early solar system's debris. Some of these Trojan asteroids may be captured Kuiper Belt objects, refugees from the outer solar system that were trapped during the planet's early migration. The discovery of Trojan asteroids sharing Earth's orbit raises intriguing possibilities for future space exploration. These objects follow Earth-like orbits around the Sun, making them relatively easy targets for spacecraft missions. They may serve as stepping stones for human exploration of the solar system, providing resources and waypoints for journeys to more distant destinations. The near-Earth asteroids that occasionally pass close to our planet represent both opportunities and challenges for humanity's future in space. These objects, nudged from the main asteroid belt by gravitational interactions with Mars and Jupiter, follow orbits that bring them into the inner solar system where they can be studied by Earth-based telescopes and visited by spacecraft. Some near-Earth asteroids are easier to reach than the Moon, requiring less energy to visit and potentially offering resources that could support human activities in space. Water-rich asteroids could provide fuel and life support materials, while metal-rich asteroids contain platinum, gold, and other valuable materials in concentrations far exceeding terrestrial ore deposits. The threat posed by potentially hazardous asteroids has motivated global efforts to catalog and track these objects, creating a census of bodies that might someday pose a danger to Earth. This planetary defense initiative represents one of humanity's first attempts to actively protect our planet from cosmic hazards, using technology to monitor and potentially deflect threatening asteroids. The successful DART mission, which altered the orbit of the asteroid Moonlet Dimorphos by deliberately crashing a spacecraft into it, demonstrated that humans now possess the capability to influence the motion of celestial bodies. This achievement marks a new chapter in our relationship with the solar system, transforming us from passive observers to active participants in cosmic dynamics. The seasonal cycles that govern atmospheric dynamics on distant worlds create weather patterns that dwarf anything experienced on Earth. The Great Red Spot on Jupiter has been raging for centuries, a storm system large enough to swallow several Earths, powered by heat from the planet's interior and organized by the rapid rotation that creates distinct bands of atmospheric circulation. These Jovian weather systems show remarkable stability over human timescales, yet they also demonstrate slow evolution as storms merge, separate, and change color over decades. The interaction between different atmospheric layers creates a complex hierarchy of circulation patterns, from small-scale turbulence to planet-spanning jet streams that of years. Saturn maintained their structure for hundreds as atmosphere displays its own unique weather phenomena, including hexagonal jet streams at the poles and periodic storms that can engulf entire hemispheres. The hexagonal pattern at Saturn's North Pole represents one of the most geometrically perfect natural phenomena in the solar system. A six-sided jet stream wider than two Earths that has maintained its shape for decades. The seasonal storms that occasionally erupt on Saturn can grow to cover areas larger than Earth's surface, creating disturbances that affect the planet's radio emissions and alter the structure of its ring system. These great white spots appear roughly every 30 years, coinciding with Saturn's seasonal cycles, though the exact mechanism that triggers these massive atmospheric upheavals remains mysterious. Uranus and Neptune, the ice giants of the outer solar system, experience weather patterns driven by internal heat sources, despite receiving virtually no energy from the distant sun. Neptune's winds reach speeds of 1,200 miles per hour, faster than the speed of sound on Earth, powered by heat flowing from the planet's interior, and organized by the Coriolis force into bands of alternating wind direction. The storms on these distant worlds appear and disappear on timescales measured in years rather than the centuries-long persistence seen on Jupiter. Neptune's great dark spot, discovered by Voyager 2, had vanished completely when the Hubble Space Telescope observed the planet a few years later, replaced by new storm systems elsewhere in the atmosphere. The atmospheric composition of gas giant planets reflects their formation history and ongoing evolution. Jupiter and Saturn are composed primarily of hydrogen and helium, similar to the Sun, but they also contain heavier elements that have been enriched by the accretion of planetesimals during their formation. These heavy elements create the complex chemistry that produces the colored bands and spots visible in their atmospheres. The ice giants Uranus and Neptune contain much higher proportions of water, methane, and ammonia, materials that were frozen into ice during their formation in the outer regions of the solar nebula. The blue color of these planets comes from methane in their atmospheres, which absorbs red light and reflects blue wavelengths back to space, creating their distinctive sapphire appearance. The atmospheric escape processes that shape planetary evolution operate differently on worlds throughout the solar system. Venus may have lost an entire ocean's worth of water through atmospheric escape, with hydrogen escaping to space while oxygen combined with surface rocks. This process transformed Venus from a potentially habitable world to the furnace planet we observe today. Mars continues to lose its atmosphere to space, with the solar wind stripping away gases at a rate that would completely remove the planet's remaining atmosphere over the next billion years. The MAVEN spacecraft has observed this process in real time, measuring the rate at which different atmospheric components escape from Mars and how this rate varies with solar activity. Even Earth experiences atmospheric escape, though our magnetic field limits this loss to manageable levels. The lightest gases in our atmosphere, particularly hydrogen and helium, can reach escape velocity and drift away into space, but this process occurs so slowly that it has little effect on Earth's overall atmospheric composition over geological time. The moons of gas giant planets experience atmospheric escape at much higher rates due to their smaller masses and weaker gravitational fields. Io constantly loses atmosphere to space as sulfur dioxide from its volcanoes is stripped away by Jupiter's radiation belts, while Europa's thin oxygen atmosphere is continuously replenished by radiation-splitting water molecules on its icy surface. The tidal heating that powers geological activity on some moons creates dynamic systems where internal heat drives surface processes, despite the frigid conditions in the outer solar system. Enceladus generates enough internal heat to maintain liquid water beneath its ice shell and power the geysers that erupt from its south polar region, creating one of the most geologically active worlds in the solar system. Io's tidal heating is so intense that it keeps the moon's interior completely molten, creating a world where volcanic activity occurs continuously across the entire surface. The sulfur compounds ejected by Io's volcanoes create a thin atmosphere and paint the moon's surface in brilliant yellows, oranges, and reds, making it one of the most colorful objects in the solar system. Europa's more moderate tidal heating may drive convection in its subsurface ocean, potentially creating the kind of circulation patterns that could distribute nutrients and energy throughout the hidden sea. The interaction between Europa's ocean and its rocky core could create hydrothermal vents, similar to those found on Earth's ocean floors, environments that might support microbial life. The magnetic fields generated by the motion of conducting fluids within these tidally heated moons create additional evidence for subsurface oceans. Europa's interaction with Jupiter's magnetic field generates electrical currents that suggest a conducting layer, most likely a salty ocean, beneath the ice shell. Similar magnetic signatures have been detected around Ganymede, Enceladus, and other potentially ocean-bearing moons. The search for life beyond Earth has focused increasingly on these ocean worlds, where liquid water persists in environments protected from the harsh radiation and temperature extremes of space. These hidden seas may represent the most common habitable environments in our solar system, existing not on the surfaces of planets, but in the interiors of moons warmed by tidal heating and possibly enriched by contact with rocky cores. The discovery of hydrothermal vents on Earth's ocean floors, teeming with life that derives energy from chemical processes rather than sunlight, has provided a template for understanding how life might exist in the dark oceans of distant moons. These ecosystems demonstrate that life can thrive in environments very different from Earth's surface, expanding our understanding of where biology might take hold in the universe. The organic compounds detected in the geysers of Enceladus and the atmosphere of Titan suggest that the chemistry necessary for life may be widespread throughout the outer solar system. These molecules, including amino acids and complex hydrocarbons, form through natural processes that occur wherever the right conditions exist, providing the building blocks from which more complex biological systems might emerge. As we continue our peaceful drift through the solar system's wonders, we discover that each world contributes its own voice to a cosmic symphony that has been playing for billions of years. The gravitational rhythms that lock moons in resonant orbits, the magnetic field lines that guide charged particles through space, and the tidal forces that heat the interiors of distant worlds all participate in processes that connect every object in our solar neighborhood. The gentle rotation of planets creates days and seasons that unfold according to the same physical principles, yet produce climates and weather patterns as diverse as the worlds themselves. From Mercury's extreme temperature swings to Neptune's supersonic winds, each planet has found its own way to respond to the energy it receives from the sun and generates within its own interior. The rings and moons that orbit the gas giants create miniature solar systems within our larger cosmic neighborhood, each one a unique experiment in gravitational dynamics and tidal evolution. These systems continue to evolve today, with new moons being discovered, ring structures changing, and orbital relationships shifting in response to the subtle gravitational influences that shape all celestial motion. The asteroids and comets that populate the spaces between planets serve as time capsules, preserving materials and conditions from the solar system's earliest days, while also demonstrating the ongoing processes of collision, fragmentation, and orbital evolution that continue to shape our cosmic environment. These small bodies connect the planets through shared histories of bombardment and through the delivery of water and organic compounds that may have been essential for the emergence of life. The magnetic fields and atmospheres of worlds create invisible weather systems that extend far beyond planetary surfaces, generating aurora, radio emissions, and particle interactions that paint space with phenomena invisible to our eyes but detectable by our instruments. These processes remind us that planets are not isolated objects, but active participants in the larger electromagnetic environment of the solar system. The solar wind that flows outward from our star creates a common medium through which all planets move, carrying with it the magnetic field lines and charged particles that connect our sun to the most distant reaches of our cosmic neighborhood. This stellar breath creates a dynamic environment where conditions change with solar activity, affecting atmospheric escape, magnetic field interactions, and the intensity of radiation throughout the solar system. The subtle dance of planetary formation continues even today, though at a pace so gentle it's measured in millions of years rather than human lifetimes. Throughout the solar system, dust particles still drift and settle, gradually accumulating on surfaces or being swept away by solar radiation. This cosmic snow falls constantly, adding microscopic layers to the surfaces of airless worlds and slowly changing the reflectivity and composition of planetary landscapes. The shepherding effect of larger moons creates some of the most intricate patterns in planetary ring systems. These gravitational guardians patrol the edges of ring zones, preventing particles from spreading outward while maintaining sharp boundaries that would otherwise blur over time. The precise orbital relationships between shepherding moons and ring particles create resonances that can persist for millions of years, like cosmic clockwork that keeps perfect time across the vastness of space. Within Saturn's rings, temporary structures appear and disappear like ripples on a pond. Spokes of darker material sometimes stretch radially across the rings, formed by electrical charges that levitate tiny dust particles above the main ring plane. These ephemeral features can span thousands of miles, yet last only hours before dissolving back into the general ring structure, reminders that even the most stable-looking systems in space are dynamic and ever-changing. The radio emissions generated by ring particles as they collide and interact create a form of cosmic static that varies with planetary rotation and seasonal changes. These sounds of space, when translated into audio frequencies humans can hear, reveal the hidden activity within seemingly quiet ring systems. Each collision, each electrical discharge, each gravitational interaction contributes to this celestial symphony that plays continuously in frequencies beyond the range of human hearing. The formation of moonlets within ring systems demonstrates how gravitational accumulation works on the smallest scales. Occasionally, ring particles clump together through mutual gravitational attraction, forming temporary moons that may survive for years before being torn apart again by tidal forces. This process provides a real-time laboratory for studying how moons and planets originally formed from the gravitational collapse of smaller particles in the early solar system. The color variations within planetary rings reveal different compositions and particle sizes distributed throughout these systems. Some regions appear blue due to the way small ice particles scatter sunlight, while others take on golden or reddish hues from organic compounds or rocky material. These subtle color differences map the history of each ring system, showing where material has been recycled, where fresh ice has been exposed, and where contamination from other sources has been incorporated. The seasonal changes that affect ring systems occur as planets move through their long orbital years, altering the angle at which sunlight strikes the rings and changing the thermal environment that governs particle behavior. During ring plane crossings, when the sun shines directly edge-on through the rings, these normally brilliant structures can almost disappear from view, revealing just how incredibly thin they really are compared to their vast extent. The gravitational influence of small, irregular moons creates gaps and waves within ring systems through resonant interactions that amplify over time. These moonlets, often no larger than city blocks, can clear entire zones within rings, or create spiral waves that propagate outward like the wake behind a boat. The precision with which these gravitational effects operate demonstrates the mathematical beauty underlying all celestial mechanics. The life cycle of ring systems spans hundreds of millions of years, with particles gradually spiraling inward toward their parent planet or being ejected outward into independent orbits around the sun. Current observations suggest we may be living during a special time in solar system history when several planets display prominent ring systems, as these structures may be relatively temporary features that come and go over geological time. The discovery of faint rings around Uranus and Neptune revealed that ring systems are more common than once thought, though they vary enormously in brightness, structure, and composition. These dark, narrow rings were detected only when they passed in front of distant stars, blocking starlight in brief, telltale patterns that revealed their presence to ground-based observers. The interaction between planetary magnetic fields and ring particles creates electrical phenomena that can affect spacecraft systems and generate unique forms of electromagnetic radiation. Charged particles trapped in magnetic field lines can interact with ring material, creating local heating effects and contributing to the chemical evolution of ring compositions over time. The study of ring dynamics has revealed fundamental principles about how disk-shaped structures behave under gravitational and electromagnetic influences. These insights apply not only to planetary rings, but also to protoplanetary disks around young stars, the accretion disks around black holes, and even the spiral arms of galaxies, showing how local studies of our solar system can illuminate processes operating throughout the universe. The delicate balance between forces that maintain ring structure demonstrates the precision with which gravitational systems can operate. The same mathematical relationships that govern ring particle orbits also describe the motion of binary stars, the precession of planetary orbits, and the complex interactions between multiple body systems throughout the cosmos. The beauty of ring systems lies not only in their visual appeal, but in their demonstration of fundamental physical principles operating on scales both vast and intimate. Each particle in Saturn's rings follows the same orbital mechanics that govern planets, yet collectively they create structures of breathtaking complexity and elegance that reveal the hidden order underlying apparent chaos. The polar regions of worlds throughout the solar system harbor some of the most extreme and mysterious environments found anywhere in our cosmic neighborhood. These regions, where planetary rotation axes point toward or away from the Sun, experience conditions unlike anywhere else on their respective worlds, creating unique landscapes shaped by eternal sunlight, perpetual darkness, or the slow rhythm of seasonal change stretched across years or decades. At Mercury's poles, permanently shadowed craters have become cosmic freezers, preserving water ice in regions that never see sunlight despite the planet's proximity to the Sun. These ancient deposits may have accumulated over billions of years as comets and asteroids delivered water to the innermost planet, only to have it trapped in these natural cold storage facilities where temperatures never rise above the freezing point. Venus's polar regions show evidence of atmospheric circulation patterns that differ dramatically from the planet's equatorial zones. The thick atmosphere creates a global greenhouse effect that maintains nearly uniform temperatures across the planet, yet subtle differences in atmospheric dynamics at the poles generate vortex structures that can be observed in infrared images as complex, swirling patterns centered on the rotational axis. Earth's polar regions serve as sensitive indicators of global climate change, with ice sheets and sea ice responding to temperature variations that are amplified at high latitudes. The seasonal advance and retreat of polar ice creates one of the most visible examples of how astronomical cycles influence planetary surfaces, as the tilt of Earth's axis determines how much solar energy reaches different latitudes throughout the year. Mars displays some of the most dramatic polar phenomena in the solar system, with seasonal caps of carbon dioxide ice that advance and retreat with the planet's long seasons. During Martian winter, carbon dioxide freezes directly from the atmosphere onto the polar surface, creating deposits that can extend nearly to the planet's mid-latitudes before sublimating back to gas during the warmer months. The permanent water ice caps at Mars's poles contain layered deposits that record millions of years of climate history, with different layers corresponding to periods when the planet's orbital characteristics cause different patterns of ice accumulation and erosion. These polar layer deposits serve as a kind of geological library, preserving information about Mars's climate variations over timescales much longer than human civilization. Jupiter's polar regions remained largely mysterious until the Juno spacecraft revealed them to be far more complex and turbulent than the familiar banded structure observed at lower latitudes. Instead of the orderly east-west flow patterns that characterize Jupiter's equatorial regions, the poles show chaotic arrangements of cyclones and anticyclones that create geometric patterns unlike anything seen elsewhere in the solar system. The auroras that crown Jupiter's poles are among the most powerful electromagnetic phenomena in the solar system, generated by the interaction between Jupiter's strong magnetic field and charged particles from the solar wind, as well as material ejected from the volcanic moon Io. These polar light shows are hundreds of times more intense than Earth's aurora and extend into wavelengths of light invisible to human eyes. As our gentle journey draws to a close, we find ourselves floating in the quiet spaces between worlds, carried by the same cosmic currents that have shaped our solar system for billions of years. Each fact we've shared tonight has been a small gift from the universe, a reminder that we live not in emptiness but in a neighborhood filled with wonders, both vast and intimate. From the sun's patient 11-year heartbeat to the delicate ice crystals dancing in Saturn's rings, from the backwards waltz of Venus to the hidden oceans beneath Europa's frozen shell, our solar system reveals itself as a place of infinite gentleness and grace. These worlds spin in darkness yet shine with their own quiet beauty, each one a note in a cosmic symphony that plays on frequencies we're only beginning to hear. If these celestial stories have helped carry you toward rest, then they've served their purpose well. The universe will continue its ancient dance while you sleep, planets turning in their orbits, moons rising over alien horizons, and solar winds carrying whispers between worlds. And when you wake, this cosmic neighborhood will still be here, patient and eternal, waiting to share more of its gentle mysteries. Sweet dreams, fellow travelers. May your rest be as peaceful as the silence between the stars.